Welcome back to reaction rates. The next thing that we'll be looking at are the two major types of energy and how they are related to the rates of reaction. The two major types of energy you'll remember from last year are kinetic energy, or energy of motion, and potential energy, or energy that is stored. The first one that we'll look at is kinetic energy. And you should also remember from last year that temperature measures the average kinetic energy of the molecules in a reaction. So, if we increase the temperature, we must also then be increasing the kinetic energy of the molecules. If temperature increases, then our molecules will be moving faster. Kinetic energy is energy of motion. If the molecules are moving faster, then they will have more collisions with each other. And we know that more collisions cause more reactions. And if we have more reactions, then overall we will have a faster or a greater reaction rate. But we know from experiment that some reactions double their rate with only a 10-degree increase in temperature. So how does this make sense? If we've only increased the temperature 10 degrees, how is the reaction doubling its rate? This is because the total number of collisions doesn't double with a 10-degree change. If you change the temperature by 10 degrees, you're not necessarily doubling the total number of collisions because of faster molecules. What you're doing is doubling the collisions that result in reaction. If you had 10 reactions to begin with, or 10 collisions to begin with, and you increase the temperature by 10 degrees, you're not necessarily doubling to 20 collisions. Maybe when you started, only 5 of those collisions caused reactions, and then you doubled that amount instead. So you're doubling the collisions that result in reaction, not necessarily doubling the total number of collisions. Only those collisions with enough kinetic energy to break bonds will cause reactions. If the collision isn't high energy enough, the bonds won't be broken and the reaction won't occur. This minimum amount of energy that's required for reaction is called the activation energy. When we're talking about kinetic energy, we refer to activation energy as the minimum amount needed to react or break bonds. If we're talking about potential energy, we'll be talking about the minimum amount needed to make the activated complex from the reactants. And we'll talk about what the activated complex is in a little bit. The activated complex is a short-lived molecule, occurs only in the middle of the step, and this is where the bonds are in the process of being broken or formed, and it's found at the top of the potential energy graph. We haven't looked at the potential energy graphs yet, but we will. We did see an example of an activated complex 2 lessons ago when we learned about collision theory. And here's the one that we had. We had the reaction where we were breaking the bonds between bromine and nitrogen and forming a bond between the 2 bromines. So this molecule was our activated complex. It was that in-between, half-broken, half-formed kind of molecule. Next, let's take our kinetic energy information and our temperature information and put that on a graph. Graphs help us to visualize what's actually going on with the molecules. So this graph is going to show the distribution of the kinetic energies of the molecules in our reaction. In other words, it will show us the molecules that have high kinetic energies, average kinetic energies, and low kinetic energies. So let's take a minute to look at this graph, and then we'll make some notes in your packet. On this graph, we have the number of molecules on the y-axis. So the higher the curve, the more molecules there are in that spot. We have the kinetic energy of molecules on the x-axis. So as you go to the right on the x-axis, your kinetic energy is increasing to the right and decreasing to the left. We have two separate temperatures for the same reaction on this curve. Just like you did with your iodine clock lab, we can run reactions at different temperatures, and each reaction and each temperature would give us a different graph. So we have one that was run at a lower temperature and one that was run at a higher temperature. This line right here, marked by this arrow, represents the activation energy for this reaction. Any molecules that have kinetic energies higher than the activation energy will be able to react. Any molecules that have kinetic energies lower than the activation energy will not be able to react. So if you look at these two curves, the lower temperature reaction has most of its molecules on the low end of kinetic energy. It has some molecules over here in this shaded area that are able to react, but the majority of them are not high energy enough to cause bonds to break during a collision. If you look at the higher temperature instead, you'll see that most of those molecules are a little bit higher on the kinetic energy scale, and there are a lot more of them that have the needed amount of energy to break bonds during collisions. These shaded areas represent the molecules that are able to react. So more of the higher temperature molecules have that needed energy. The lower temperature molecules are mostly over here. They don't have enough energy to react. Only a few of those have enough energy to break bonds during collisions. So let's write down what we just talked about. The symbol E subscript A is the activation energy. That's the minimum amount of energy needed. The area under the curve to the right of the activation energy, that was the shaded part, represents the number of molecules that are able to react upon collision. The higher temperature area is larger than the low temperature area because the higher temperature is faster, because it has more high energy molecules that have more high energy collisions. And third, remember that this curve changes with temperature and it changes with reaction. So every individual reaction at every individual temperature would have a different curve. Let's look at that graph one more time just to be sure we understand. Number of molecules on the Y, kinetic energy on the X. Anything past the activation energy has enough energy to react. The higher temperature curve has more molecules past the activation energy than the lower temperature curve. This means the higher temperature curve has more reactions, and so it has a faster rate. Two things we can conclude from this. More collisions occur due to faster velocities of molecules at higher temperatures. And two, when that happens, more molecules have the minimum amount of energy required to react. Time to switch gears. Now we'll do potential energy diagrams. We did potential energy diagrams back in thermodynamics last spring, but we didn't put numbers on them the way we'll do this time. We'll do one for an exothermic reaction and one for an endothermic reaction. This time we're going to have data points to plot, so we'll be given 3 pieces of information for each graph. The potential energy of the reactants to start with, the potential energy of the products when the reaction is done, And on this one, we're given that the activation energy is 200 kilojoules per mole. This tells us how much more energy we need in order to get that reaction to occur. Let's put that on a graph. We have potential energy in kilojoules per mole on the y-axis. And just like last spring, we have the progress of the reaction on the x-axis. That means we're going to start with our reactants on the left and progress to our products on the right. We have reactants. In the middle, we have the activated complex. Remember, that's halfway through the reaction or partway through the reaction, half broken, half formed kind of molecule. And then on the right, we have the products. Our given information said that the reactants started at 200 kilojoules per mole. So this is our baseline. This is where we started. We needed 200 more kilojoules per mole to make the activation energy, or to make the activated complex. And then our products ended at 100 kilojoules per mole. Connect these points with a mostly smooth curve, and you have your potential energy diagram. Remember that this activation energy is almost like the hurdle that the molecules have to jump over before they can react. The reactants started here at 200. They need to be up here at 400 before they can react. And then the products end up being lower than where the reactants started because this is an exothermic reaction, so we have to have energy released. So between 100 and 200, there's 100 kilojoules per mole of energy released by the products. Let's write down a few notes. This curve is a characteristic of the reaction and does not change with temperature. This curve applies to the specific reaction, but not the temperature that it's running at. If you were to run it at a higher temperature, you would simply have more molecules jumping over that barrier of the activation energy, but the graph itself would remain the same. Note number 2, the point of highest potential energy on the graph is the energy required to make the activated complex. So, the potential energy of the reactants plus the activation energy is the potential energy of the activated complex. This is where we got the 200 plus 200 more was 400 kilojoules per mole. Note number 3. Again, last spring in thermodynamics, we learned about delta H. Delta H is called enthalpy. And enthalpy represents the heat of reaction, or the amount of energy that is released or absorbed during that reaction. Delta H is found by taking the potential energy of the products and subtracting the potential energy of the reactants. Final energy minus initial energy. We did this last year, although only for a day or so. For this reaction, we would take 100 kilojoules per mole minus 200 kilojoules per mole. Delta H ends up being negative 100 kilojoules per mole, and the negative, remember from last year, means that energy is being released or energy out. Next, let's do the endothermic reaction. And you probably know the endothermic is going to be almost the opposite of what the exothermic was in a couple of ways. Here's our given information this time. Potential energy of the reactants is 300. The products is 600. And this time, we're being given the energy of the activated complex. This is different than the information you got last time. So it's going to change how we make our graph. We will keep potential energy on the y-axis and keep the progress of the reaction on the x-axis. Reactants activated complex, products. Reactants were at 300, activated complex is at 700, and there's the difference in making our graph. And the products were at 600. Connect your dots, draw your baseline, and now you can describe this reaction. The activation energy this time is the amount that it took to get from 300 up to 700. So the activation energy for this reaction would be 400 kilojoules per mole. Delta H is where you have the baseline up to the products. Products were at 600, our baseline was at 300, so delta H is 300, final minus initial. It's positive this time for an endothermic reaction. Delta H is positive. This is partly because this is the opposite of the exothermic reaction, but it should make sense because positive means energy in.